Hello and welcome. We're going to discuss graph traversals. This will be probably kind of a short video, but that's okay. There are lots of different ways to traverse a graph, and just depending on your needs, there might be different things you want to do. Um, but really, what it comes down to when we want to traverse a graph, is it depends what kind of representation you want, and also, um, yeah, like what kind of how you would like to sort of present the data. And so you have to kind of think about it uh, depending on what it is that you're trying to determine. So some problems that you might want to try to solve, um, once you know sort of how to iterate through nodes, is something like which two vertices are furthest apart, or something that is more just like print every edge once, or not even print every edge, print every unique pair of connected vertices. So this one is simple. This one is also simple, but requires a basic understanding of one. So we're going to actually start with, we're actually going to start with this right here. Now, of course, depending on the implementation of your graph, you may have like different logic that you need to consider. But effectively, what we're going to try and do is we're going to go for every single node that we have, we are going to look at what it's paired with and ask if we've already printed that information or not. So most likely what that means is we will store that information somewhere else and then run a second loop to print everything out after. So often how we will want to do something like this is we're going to want to keep some kind of a list of visited edges. So some kind of list of visited edges, and each edge has like a vertex 1, like a starting vertex, a vertex 2, and possibly a weight if our edges are weighted, right? So right now we can pretend like each of these are weighted as 1, but it's possible that they would have other weights on it. And that is true for its implementation as a matrix or as a list. So what we want to do is we want to keep a list of visited edges. Now, depending on what you know about your graph, you may know that like your whole graph is connected. You may not know that. You may know it's complete. You may not know that. There's lots of different sort of different starting points. For example, in our assignment, we know that our graph is going to be connected. We don't know how, we don't know if it's complete, we don't know any of that, but we do know that there are no like lone floating nodes over here or like a floating pair of nodes. We're not going to have that problem. And so knowing that is helpful because it means that when it comes time to start this algorithm, we can just pick a place to start. We can just pick a node to start at. And if this was going to be stored in like a matrix or a list, they would be stored in spots like I equals 0, or in the array index 0 first. So 0, 1, 2, 3, 4, and 5, right? So we have 6 nodes that are probably stored in some kind of data structure that are labeled 0 to n minus 1, most likely, with what we learned in the previous video. And so we can just start at node 0. Like there's no reason why not to just start at node 0. So we have our list of visited edges, and let's start by standing in node A, or node 0. So I'll draw my little person that I like to have, and she is right here, and she's starting right here. And so what is she actually going to do? Well, she's going to start here, and she's going to say, who am I connected to? And she's going to go and look and see who she's connected to. And she sees she's connected to B, and then she's going to ask, have I already found a case where A connects to B? If yes, ignore this. If no, add it to my list of connections. So find, or I guess I'll, instead of saying it like that, I'll say for all edges out of my current node. In this case, it's A where I start, but for all edges out of my current node, or I'll just, yeah. This says start by standing in node A, but if I was going to write this more generically or more like algorithmically, I guess I would probably say for each node I in my graph, I'm going to go ahead and I'm going to look at all the edges coming out of my current node I. And I'm going to ask if the end vertex of this edge is a vertex I already know about. I'm just going to say, screw you, go away edge. Because we're looking for, don't forget what we're looking for. We're looking for unique pairs of vertices. And we already know about this pair of vertices. Screw you, go away edge. I know that vertex. Cool. That's super professional coding. Otherwise, we're going to say cool new pair of nodes, add to a list of visited edges, because that's going to be an edge that we want to keep track of. So our list of visited edges will kind of grow as follows. So let's walk through this. We start with our person here, and she finds this edge and she sees that our list of visited edges, the only is empty, right? Like she sees that we don't have any visited edges yet. So we're going to add the edge AB to this list of visited edges. We have finished traversing all the edges that come off of this node. So now we're going to go to the next node. We go to this node and we're going to look at every single edge coming off of this node. First, we look at BA and we see that that edge already exists. So screw you, edge. I don't care about you. Then we're going to go and we see BC and we go, we don't have that edge yet. Ah, sweet, new edge. And we're going to go ahead and add BC to this list. Then we're going to go to BD. Ah. Uh-oh, I put that. Now I've put that person in a place where I can't pick them up because sometimes notability is silly like that. Let me re-add BC here and continue with my algorithm. We come over here and we have to do BD and we have to do BE, and we can see that both those edges exist, and both those edges one by one I would notice are not in my list of visited edges, so I would add them and then I would move here. So let me add BD and BE. This is like a brute force algorithm. Like this is not efficient, obviously. Okay, then I'd be standing at C and I would look and find for each of these edges, I'd go here and say, well, is there a BC pair of edges already in my list? And the answer is yes, it is. So screw you, I'm not picking you up. And then I'm going to go down and see CE. Does CE exist yet? And no, it doesn't exist. So I will add that also to my list, CE. I've gone through all of my potential edges on C. So now I'm going to go to D. DB, does that exist? Yes, it does. DE, does that exist? No, it doesn't. Get that added to my list. DE. Then I'll go to E and I'll say for each of these edges, does BE exist? Yes, it does. Does CE exist? Yes, it does. Does DE exist? Yes, it does. Does EF exist? No, it doesn't. I'll go add EF, and then that will be all my E edges. And then I can go to F and find the single edge and see the EF already exists. So screw you, I'm done. And that algorithm ends. And my list.size 1, 2, 3, 4, 5, 6, 7. I have 7 uniquely paired connected vertices. So we can see how we can start to walk through each of those edges. Now, that was brute force, right? We checked lots of edges over again that we'd already checked. We had to search through this list here for edges each time. So this was like brute force in the least efficient way possible. This could be done in smarter ways. We could use like a hash set to keep track of my list of vertices. And then that way it's an O of 1 lookup to see if I already have visited that edge or not. And here we cared about going to every single edge, but we didn't care which route we took. in my next video, we're going to talk about actually caring about the routes that we take and what those algorithms might look like instead. Because here we didn't care, we just wanted to visit everything at least once. And what we ended up with was visiting, I'm just going to actually highlight the edges that we found and we kept. We found AB, we found BC, we found BD, we found BE, and we found EF. So those are all the edges that we actually found and we kept track of after finding in that list. And what you'll notice is that while the original list had cycles in it, because we're keeping track of unique data points here, our new list does not have any cycles in it at all. In fact, we found a tree inside of our graph. So this subgraph of unique edges only, unique pairs of nodes, ends us in a tree. Now, again, all we cared about was whether or not we had already visited nodes. We didn't care about things like the weight of our edges. We didn't care about the priority that we considered for our edges. When we look at our minimum spanning tree, we will care about that. And then when we look at our Hamiltonian cycle video, we will care more about the cycles. So finding these non-unique edges and how that affects things. But let's just look at one more example of traversals instead for now. And then of course, you can consider this idea of which two vertices are furthest apart and how you might want to do that. Because what we just did is we, in theory, walked every single edge. We started at A and we said we have to walk A and B. And then there was nowhere else to walk off of A, so we came to B. And then we went from B, we walked in every single direction, only going down ways that we hadn't already gone. We already did A, so screw you A, we came over here. Then we did C and we walked each of these directions. And then we did D and we walked each of these. Then we did E and we walked each of these. Then we did F and we walked each of F's. And so what we could do is, in building out this list here of walkways, is we could figure out our furthest path. We could walk from A to B and get that path. We can walk from A to C and get that path. We can walk from A to D and get that path, from A to E and get that path, from A and F and get that path, and keep track of the number of edges we traversed for each of those. Then we can go to B and do the same thing. B to A, does that beat our current maximum? No. B to C, does that beat our current maximum? No. Does B to D, does B to E, does B to F? Keeping track every single time of our current maximum, starting from C and walking down every edge possible to get to where we want to go, starting from D and walking every edge possible where we want to go. This is a very naturally recursive problem. This problem involves basically for every permutation and combination that we can find of pathways to walk, what are we going to end up with? So it is like a permutation and combination problem. If you watch my videos from 1020 recursion on YouTube, you'll actually see some more conversation around solving permutation and combination problems, because each step of this recursive problem allows us to sort of consider every possible avenue off of that step, and every possible avenue off of the next step, and every possible avenue off the next step, and et cetera, until we sort of backtrack our way back through with a final answer. So it is kind of, this other one here is definitely more of a complicated problem to solve than just this one. But hopefully as you start to play with this code and how things connect to each other and how we can move through it, the implementation of these things becomes clearer. Now I just have one more example here, because again, we want to find unique pairs of nodes, but here we also, it turns out, would have to consider something like the direction, which we didn't previously. And I don't even actually want to show it with the adjacency matrix, because that's one way to do this, but it's not the only way, right? We could solve this problem right here with an adjacency matrix or an adjacency list, and we can solve it for directed or undirected, and we can solve it for weighted and unweighted. All of those things are independent variables of each other. So if we just look at this here, thinking of our algorithm, it would be very similar, where here on 0, we would just look at both the edges that exist and if it's an edge I can walk. So this edge exists and I can walk it, and I haven't done it yet. So 0, 1 is something I'd keep track of. But this edge I can't walk and this edge I can't walk, so I'd be done. And all I would have found is 0, 1. Then next time that I run through, I'd move to 1. And here I would find 1, 2, 3, 4 edges. I'd find I can't walk this edge, right? In an adjacency matrix, it's especially, actually in both implementations, it's especially obvious. But in a drawing, it's less obvious. We have to actually explicitly say I can't walk that edge, but I can walk this edge, but that edge already exists, so I ignore it. I can walk this edge. It doesn't exist, so I found 1, 3, and I can't walk this edge. So we're going to just add 1, 3 to our list. Okay, we come down to 2. We look at 0, 2. This edge can be walked and doesn't exist. This edge can be walked and doesn't exist. This edge cannot be walked, even though it exists. So I have found 0, 2, and 2, 3. 0, 2, and I guess it's not 0, 2. It's 2, 0, and 2, 3. Then we move on to 3. I'd find this edge that can be walked, but I already have that pairing. I'd find this edge that can't be walked. I'd find this edge that can't be walked. I'd find this edge that can be walked and does not yet exist. 3, 4. And then I would go to 4. I'd find this edge that can be walked and does not yet exist. I'd find this edge that cannot be walked. It exists. It doesn't exist, or it exists already anyway. And I'd find this loop that I have not yet traversed either. So what have I found? I have found 1, 4, and I have also found 4, 4. So by like drawing a little person and walking my way through my graph, I can start to build out what that algorithm might look like. Okay, so that is some sort of ideas of traversing through our graph. We are going to next look at minimum spanning trees and Hamiltonian cycles in 2 separate videos where we will further discuss what it means to walk through these graphs and what other data structures we might need to help us walk through these graphs appropriately. All right, thanks everyone, and see you in my next video.